C'est un grand plaisir pour moi de vous présenter le professeur Yehuda Afek de l'Université Tel Aviv, qui va présenter un travail commun avec d'autres auteurs, dont certains dans la salle et certains sont passés par le PFL. Certains d'entre vous ont assisté au cours de Vassos Atziliakos, qui avait présenté les hiérarchies de consensus de manière incroyablement élégante. Et en fait, c'est un sujet qui est toujours d'actualité, où il y a pas mal de gens qui cherchent encore, et je pense que le travail que va présenter Yehuda Afek s'inscrit dans cette lignée-là.
Thank you. Thank you very much for inviting me, Rachid. Must tell you that coming here after having election in Israel, coming to Paris,
It was election or what it was test and set?
We don't want to discuss what it was, but I prepared the slides to the talk during the election. The election is a vacation day in Israel, and the results came in the middle. So if the slides all of a sudden deteriorate, there's a reason. So the topic, I have no biology, no connectomics, no flies, no birds, no zebras. Very small world, very simple, very technical. We have computers that communicate with each other by shared memory. They can interact by either writing or reading into shared memory or doing other operations on the shared memory. It's really machines, Intel machines, communicating on the shared memory of the different cores or other clusters of machines. And we want to know what is the power that it gives the communicating computers when they interact in the shared memory. So the beginning, like the first half of the talk, it will be boring for half of the audience at least, if not everybody, because it's very known material. And then I will hopefully give some new information. So we measure the computability power of computers that interact by the ability to solve a task. What is a task? A leader election is a task, for example. Or we'll see other tasks. We have, so that we classify deterministic objects. We consider only objects that you can model the behavior of the object by a state machine. So the interaction is concurrent. Each process makes an action on the state machine, but the machine state is deterministic on the serialization of the operations on the object, the shared memory object. So the object sits in the memory. Atomic registers is an example of a deterministic object, stacks, queues, compare and swaps, and so forth. The tasks we consider, ignoring the vector notation, is like consensus. Everybody has to agree on an input, set consensus. We'll see them in a minute. So that's a state machine. And we want to classify them by the computers, by the power of each communication primitive to solve a task. The model will be standard asynchronous shared memory, deterministic object, and we're interested in tasks that can be solved when no computer has to wait for other computers. They can do it wait-free. And all processors can be shut down. One processor will still solve the problem. So early, already 20, 30 years ago, it was considered by Maurice Hurley and others, the consensus number of an object. A shared memory object is measured by how many processors, when communicating with many copies of this shared memory object, can solve the consensus problem. What's the maximum number that can solve it? So the consensus number is C. If C processors communicating with such an object can solve the consensus number, C plus 1 cannot solve the consensus problem. And already in the beginning of the 80s, 1986, 7, not the beginning, the end, Maurice Hurley created the Hurley hierarchy according to consensus numbers. So you have registers. Which button do you push here? I don't know. Here. You have registers that One processor can solve with himself, but trivially he agrees with himself. Two processors cannot reach agreement with communicating, weight-free agreement, communicating with shared registers. All of these objects allow two processors to reach agreement. Three processors cannot reach agreement. And in each level of the hierarchy, there is an object. And finally, compare and swap, or load, link, store, conditional, are shared memory objects that allow any number of processors to solve consensus. This is very well known to many people here in the audience. And actually, Intel machines or any machines that we use today, they do have these objects in their language. They do need these actions on the shared memory in order to be able to do concurrent computations on multi-core machines or communicating through the memory. So what do we know? If an object, the consensus number of an object in the hierarchy is smaller than the consensus number of another object, then there is no way to implement one from the other. You cannot implement a test and set from registers. There is no way to write a code so several processors can reach test and two processors can reach test and set by just reading and writing on registers. Or any level of the hierarchy. You cannot implement a higher level from a lower level object. However, there is kind of a universality. All the objects, any object in a level k of the hierarchy, say k equal 2, can implement any object for that number of processors. When the number of processors equals to the consensus number, they can do everything. Specifically, each object in the end can solve all the problems, linearizable objects, in a weight-free manner. And there is the question, can every element in the certain level can implement each other for a number of processors which is larger than k? Can n processor system with a test and set implement swap? We see that it's possible. We'll see it in a minute. So we saw it in the beginning of the 90s, 1994, 1995. You can do test and set from two. Each of them can solve two consensus. That's the definition. So if you can do from two consensus, any of them, you can do it from all the others. We can do swap from two consensus. We can do stack from two consensus. Can we do Q? We don't know. It remains open. So about 3 years ago, Ellie and Faith Ellen worked on the problem of, let's see, what's happening between these layers. Common two is all the objects that can implement each other with a consensus number equal 2, and so forth. And we showed that it's impossible. There is no common two, and the consensus hierarchy conjecture that all the objects in a certain level can implement any object for a larger number of processors, but with consensus number k, is false. Let me spend a few slides to explain it. For this, we introduced a new task, the set consensus task, where processors have to agree, but they can agree on k different values out of n. So here, n processors have to agree on k different values. The task is non-deterministic by nature, because if it's deterministic, it becomes a consensus. It must be non-deterministic. And there have been proofs by Hirli Shavit, Borowski Gafni, and Sachs Zaharoglu, beautiful works using topology that show that atomic read-write registers cannot solve weight-free set consensus. So Borowski and Gafni continue to find the relations between different set consensus objects. So basically, if you take Lj smaller than n and k, and you take many copies of L, how many L's enters n, so n over L, times you decide on J, you can get K. So it's easy to do K set consensus out several copies of the LJ set consensus, and they get this relation. But sometimes there is remainders, and the numbers don't divide nicely. And they did the more precise work and got the exact relations between the different set consensus objects. And what was done by Ellen and Gaffney in 2016, Ellie suggested actually a new object. And you see, this is a deterministic object, very strange one. So it has how many states? 1, 2, 3, 4, 5, 6 states, at least as I do it here. You start here, some process suggests A, he gets A as a return. The next process, or whatever it proposes, gets A back, the value of the first one. The third process suggests B, he will get back B. The fourth one will get the B of the third one, and the fifth process to make a propose will get the value of the first one. So it is called AABBA. Understood? That's the state machine. The consensus number of this object, if you look here, just consider these two states, is 2. Just take the two processors, the first and the second, reach agreement. So it has 2-1 set consensus, which is like a 2 consensus. The set consensus, if you take 5 processors, they can reach here 2 set consensus, decide on A and B with 5 axes. If we consider the relations we saw before between the different set consensus that Borowski and Gaffney did in 1993, we get that the consensus number cannot implement the set consensus number. So this object has consensus number 2, but consensus number 2 cannot implement this object. So maybe it has 3 consensus. The consensus number of this object is maybe 3. No, it is shown in the paper from 2016 using bivalency arguments that the consensus number is smaller than 3. So it is 2. The maximum number of processors can reach agreement is 2. And this is a counterexample for what we asked before. In the level 2 of the hierarchy, here is an object whose consensus number is 2, but consensus number 2 cannot implement it because of the set consensus value. 5-2 cannot be implemented from 2 consensus. So the consensus common 2 conjecture is false. And the paper continued to introduce more objects, and with a larger, you can play with the number of letters and with the number of repetitions of the letters, and we get infinite hierarchies of objects that break the conjectures for each level of the hierarchy. Each level of the hierarchy has an infinite number of objects, deterministic objects, that refute the conjecture that they can implement each other for any number of processors. So you can see these 2 hierarchies. The Hurley's hierarchy use deterministic tasks. The new hierarchies use non-deterministic tasks, but it refined the Hurley's hierarchy, a real refinement of the Hurley's hierarchy. But one question was left open.
What is deterministic and non-deterministic task?
Set consensus is not deterministic because I can return either of the previous values. It's not deterministic.
There is no definition for it. I don't know what it.
That's, I have to teach the teacher what he taught me.
There is no definition. I haven't seen anybody defining deterministic and non-deterministic tasks. There are objects.
Anyhow, so what happened here? Here are there deterministic objects in the level 1. What is level 1? They cannot do consensus, but is there a deterministic object stronger than read-write register? Read-write registers cannot implement it, but it cannot do 2 consensus, and it is a deterministic object. Eli and many others conjecture, no, there is nothing. We thought it's empty. It's either registers or two consensus for deterministic.
So this picture, this black line shouldn't be there. This is the question. The question.
Which black line? I don't see a black line.
There is nothing below read-write. There is the question is whether there is something between 1 and 2. So the picture is misleading.
You mean this read-write register?
There is no question about inside the white one. It's in between the white one and the first.
It's understanding pictures. How am I doing on time?
You have 2 more minutes if he
Because
stops.
of Eli.
And 20 minutes otherwise. Okay. So what we did in this new work, Eli and another Eli and Giuliano, a student of Rachid, we defined a new object, a deterministic object. It has K cells, registers, initially bottom. When you invoke an operation with an index I, you write the value, the input value, into AI, and atomically, all of this done in one atomic step, you read the value on the location in the register I plus 1 mod K. So for example, if 3 cells, I invoke an operation, I write 14 and read the A1, for example, or if we do like this, you can see that this processor, he wrote 8 and read whatever was already in A0. Okay, it's a deterministic object. In one atomic step, you write one cell and read another cell in a cyclic order. So to show that this is really an example of something in the level 1 of the hierarchy, you have to show that it's not possible to implement it with registers, and that it's weaker than 2-set consensus. So we know that if it's stronger, to show that it's stronger than register, if you solve set consensus, we already know it will be strong because of the topologies proved. So it's very simple to solve set consensus with this object. It's almost immediate. Every processor here goes. You read each other. The one that the last one to do the operation, he will get a value from the previous one because already he sees in the other, and the other two may return bottom. So if you see bottom, you return your value. If you see something, you return whatever you saw. Necessarily, the last one to do the access, to write and read, will get a value. So there you are. We can do it also if they don't have indices between 1 and 3 or 1 and n by doing all kinds of combinatorial tricks. We'll skip it. It's weaker. We use bivalency arguments to show also that it's weaker than 2 consensus. So I skipped the how much time do we have? 5 minutes. Okay. If any brutto or netto. Okay. So we skipped the, but you can see the bivalency argument. You get to the critical states, those that are familiar with the FLP. At the end, it's like a read-write because we must intersect on something. So I probably wrote there and you read from there. But then it's like the behavior of read-write registers. So it cannot do, intuitively, it cannot do consensus. So we are done. We proved that it is an object exactly like we suspected that doesn't exist. And we actually further worked and managed to build a hierarchy. What about a hierarchy of objects? And we used a one-shot variant of this object, slightly weaker, in order to prove rigorously a hierarchy, infinite hierarchy of objects inside that level 1 of the hierarchy. I skip the details. So to prove that there is a hierarchy, you would prove that we can, this one does the strong set consensus. This we showed already before, and use BG to see the relation to these two, and we got the tight relations between K and K plus 1 copies of this object. So there is an infinite hierarchy of deterministic. Are we done? Not really. If we look what we have done, Here are the number of processors, and this is the set consensus, and here we'll put objects that can solve these problems, that for 4 processors, 2 set consensus, or for 4 processors, 5 set consensus. Is meaningless, right? So all of this area is pretty meaningless because you have fewer processors than the set consensus. So we saw that for 3 processors, 2 set consensus, we just solved with these 3 cells, the 1, 3. And you can do same for 4, 3, 5, 4, and so forth. Can you do anything else? Can you do 5, 2, 5, 3, something? Can you do something else in this diagram? Surely you can take 2 copies of 3, 3, 2, and you get 6, 4, which is already by the Borowski-Gaffney relation between same consensus object. You moved a little bit stronger. And similarly, you can take 2 copies of this. So you already done some improvements. More than that, maybe Eli has the solution in his pocket, but I'm not aware, and Eli says he is not aware of any object, deterministic object, that will do any way to generalize, to extend the warrant. We have no idea how to do it. We don't know how to do a deterministic object that has 5-2, 4-2, 5-3 between, but probably there is one, but we didn't find it. So we've seen this, we solved this, and the key, something that took me a while to realize, and many days with Eli, and then you realize it, that consensus and set consensus are 2 independent parameters of an object. And actually, if you go, there is a paper already, I don't know what year, it was probably 5, 6 years ago, by Carol, Hug, Eli, and Peter, that already suggested that there is, to really understand what is the power, communication power of a shared memory object, you have to have a vector of its powers to solve consensus, 2 set consensus, 3 set consensus, and so forth. What is the number of processors you can solve each of these tasks? So what is the maximum number of processors this object can do consensus to? What is the maximum number of processors this object can do 2 set consensus, and so forth? And they suggest, Carol, Hug, Eli, and Peter, that such a vector describes, fully characterizes an object. There are papers claiming it's incorrect, but their proofs are not really tight and simple, and they probably use non-determinism, suspect so. So we don't know. Is this characterization? It's like a generalization of the consensus number. Consensus number was just one number. What they say, actually you need a vector of numbers to characterize a shared memory object. And we need to prove now this much more richer hierarchy, if it's correct, if it exists. And maybe we'll see it in the afternoon, I don't know. Okay, so that's the definition I just described. I didn't know I have the slide. So we saw the table with the remaining open problems, the problem of understanding the hierarchy defined by the 4 authors, Carol, Hug, Eli, and Peter. Is that the hierarchy? Is this will be the true hierarchy for deterministic objects? We don't know, but maybe it is. Okay, thank you very much.